Okay, so we're going to do L'Hopital's rule. L'Hopital's we've already done, so hopefully this goes pretty smoothly. F and G are differentiable. If the derivative of G is not equal to 0, just because it's in the denominator, you can't have 0 in the denominator, then you can use L'Hopital's rule. Okay, so if you have an indeterminate form, so if it's 0 over 0, or I would add here plus or minus infinity over plus or minus infinity, then you can take this limit. So if you directly substituted a in and you got 0 over 0 or plus or minus infinity over plus or minus infinity, then what you do is I put a little h on top of the equal sign to say I'm using L'Hopital's, and you just take the derivative of the top piece and write it on the top, and you take the derivative of the bottom piece and you write it on the bottom. So am I using quotient rule? No. Okay, every once in a while I get someone who's like using quotient rule. That's not what this is. Okay, you just take the derivative of this, put it on top, take the derivative of this, put it on bottom. So questions on it? I know we've done it, so let's just jump into some problems. Okay, this one is really nice and quick and easy. Our hint here, plug 0 in for x and see what you get. If you get 0 over 0 or infinity over infinity, you can apply L'Hopital's. The only thing, and we talked about this before, if L'Hopital's applies, you need to write therefore L'Hopital's applies. So if I plug in 0, I get 0 over 0, therefore L'Hopital's applies. Not that I know of. And different books spell L'Hopital's differently, which seems crazy to me, but they apparently don't know how to spell his name, so. This book does L hospitals, but I've seen it spelled not like hospitals in the back, whatever. They'll know who you mean. So once L'Hopital's yeah, so maybe but your name shouldn't change spelling, you know? Is it spelled like this? Yeah, but different books spell it different ways. I don't know. It's just weird to me. Okay, so let's apply L'Hopital. So we'll just do this. This is what this book does. So we've got the limit as x goes to 0. That doesn't change. Then you do the top derivative is 2x. The bottom derivative is 1. And what happens when you plug in 0 now? Just 0, right? Okay, so these are warm-up problems. Go ahead and do 2 and 3. And we'll just check our answers on those ones and see if we need to explain them. Okay, so we get 2 for this one here, 0 for this one here. Same idea as the first one. On this page, they just get a little more difficult. It's not like they're crazy difficult, and there's different ways to think about them. But here we're going to be approaching negative infinity, where back here we were approaching a number instead of an idea here. But if we plug in negative infinity, what would this be? E to the negative infinity. E to the positive infinity. Okay, now this E is like 2.7-ish, right? So if you're talking about going to infinity, it's just a exponential graph. So e to the infinity is infinity. Questions on that at all? So this is giving me infinity on top, and negative infinity squared is also infinity on the bottom. Therefore, L'Hopital's applies. Okay, and I do want you to write that every single time you use it. It'll help remind you to use it on the AP test so you get your points there. Okay, so now we're going to use or apply L'Hopital's. So we leave the limit part alone. And the derivative of e to the negative x is negative, good, over 2x. What happens here? Yeah, you get negative infinity over negative infinity. Therefore, L'Hopital's applies. So you just take this and you just clone it, you know. And just shift it over here. Throw a negative in the front. There we go. So then we're going to apply L'Hopital's again. And the derivative of the top here is 1. Back to positive e to the negative x. And the bottom, 2. So we should not be applying L'Hopital's again after this. So the numerator is what? Infinity, and the denominator is 2. So what would I write for this then? What's infinity divided by 2? Still infinity, so it is does not exist is probably what the answer key will say, okay? So if you get infinity and the book has does not exist, it's because technically it does not exist. Okay, and you could even, I would kind of encourage you to go back here if this is on the AP test and erase this step and this step in case your sign is wrong. Because you're going to get your point off if you have the sign wrong here, but you'll get full credit for your answer if you have this here, okay? So go ahead and try 5 and 6. With 6, you have to get it so that there's only one fraction, so I would work on a common denominator there, but I'll give you guys a few minute head start there. Okay, so number 5, you move e to the negative x to the denominator, and then you apply L'Hopital's. You end up with 0 there. With 6, the first thing I would do with 6 is get a common denominator. That's what you guys did, right? So a common denominator would be this times this. So if you have that, this first piece would be x minus 1, and the back piece would be minus the natural log of x, because it's subtracting it all over this. And this is scratch work right now. If you want it to be, you know, the limit piece, you can just write it down here, put the limit in front. I would kind of encourage you not to use a bunch of equal signs for different parts here. But we're approaching, does it say 1 from the left, correct? From the right? Okay. There we go. Switch that. Okay, so if we're approaching 1 from the right, this is like 1 minus 1 minus the natural log of 1, which would be 0 on top. And on the bottom, this is 0 times 0, so 0 on the bottom. So I get 0 over 0, therefore L'Hopital's applies. And we're going to apply L'Hopital's then. So we're approaching 1 from the right still. The numerator, this turns into just 1 minus 1 over x. And the denominator, you have to use what rule? Product. So product rule, leave natural log x alone. And the derivative back here is 1 plus the derivative of natural log x is 1 over x times x minus 1. And you can clean that up first, or you can just multiply the top and bottom by x. That's the quickest way to do it. So if we do that, now we've got the limit. The x turns into x minus 1 on top. Let me know if I make an error here. The bottom turns into x natural log of x plus, and if you multiply the back piece here by x, this piece just goes away, so you just get x minus 1. Questions so far? Does that all look accurate? So then we plug in 1 again. On top we get 0. On bottom we're getting 0 plus 1 minus 1, so 0. So 0 over 0, therefore L'Hopital's applies. That's not what I wanted. And we go ahead and apply L'Hopital's again. So the numerator is going to turn into just 1 now, right? And the denominator here, you have to use product rule. So leave the x alone times 1 over x plus take the derivative of x, which is 1, and leave the natural log x alone. And then plus 1 because of the plus x back there. So this would just turn into 1 over 2 plus natural log x. You guys okay with that? Does that look like what you had? And then if you plug 1 in, natural log 1 is 0, so you just get a half there. Any questions? It's pretty good, right? Okay. Now back here, these are kind of a different story. So I think I drug the hint on before I printed it, right? So when you see an x in the exponent, set the problem equal to y. So your answer is y, so make sure you solve for y at the end. That's something that maybe you want to highlight or kind of make note of here. Okay, your answer is y, so make sure to solve for y at the end. Otherwise, you end up with the wrong answer, and that's really annoying because you did all of your work, you just didn't finish it out. Okay, so then take the natural log of both sides, just pulls the exponent out front. So what we're going to do here is exactly what that says. We're going to set the problem equal to y, so we're going to say y equals this. Then we're going to take the natural log of both sides. So we're going to natural log this side and natural log this side. So questions on this? We kind of did this in a different unit. We're not using L'Hopital's yet. Okay, so we will be proving that L'Hopital's applies when we get to that spot. Okay, this is just to get that x out of the exponent so we can actually do something with it. Because right now if you plug in infinity, you get, and this is like weird to try to even figure out, you would get 1 plus something really close to 0 to the infinity power, which seems like it might be 1, and it seems like it might not be 1 because this is slightly bigger than 1 and it's raised to the infinity, so that could actually come out to anything. So with something like this with the x and the exponent, this is the way to actually get to an answer. There is a different case later on that we'll talk about, but this, to do problems like this is how you're going to have to go about it. Okay, so if I take the natural log and ignore the limit for the moment, what can I do with that x power? I can pull it down, right, because of laws of logarithms. So we've got natural log y equals x times the natural log of 1 plus 1 over x. So any questions before we start doing the problem here? Okay, so now I'm going to go ahead and I'm going to add in the limit. So let me just move this piece over here to save myself a little room. Okay, so I'm taking the limit as my x is approaching infinity of natural log y. That's equal to the limit as x approaches infinity of this side here. Okay, and now I'm just going to work with this side here. So I want to apply L'Hopital's probably because that's the section I'm in. If you just tried to plug in infinity right now, you would have infinity times 0. Isn't that what that would be? And infinity times 0 is kind of a weird case because you have something infinitely large and infinitely small working against each other. And it could fall at infinity, it could fall at 0, it could fall anywhere in between. So that is an indeterminate form. You can't actually do anything with it. So what I'm going to do is I'm going to move this to the denominator. So if I move that to the denominator, it's going to turn into x to the negative first, right? Or 1 over x. And now if I plug in infinity, I can apply my L'Hopital's because I get what on top? 0. And on bottom, I get 1 over infinity, which is 0. So any questions so far? Okay, so I'm going to go ahead and I'm going to apply my L'Hopital's here. Okay, so taking the derivative of natural log of something, it's 1 over that something, right? And this is getting really pretty now. This is turning into an AP Calc BC problem. I like it. And then you still have to multiply by the derivative of the inside. What is the derivative of the inside? Negative x to the negative second, or negative 1 over x squared. I'm just going to leave it like that because it's going to actually work out really nicely here. It doesn't seem like it will. But what's happening in the denominator? Negative 1 over x squared again, right? So these will cancel each other out. So questions there? Let's go ahead and finish this out. Now it's not anything tricky. And you don't even have to clean it up if you don't want to. Don't you just get 1? And a lot of people circle 1 and say that's their answer. Remember back to the hint, didn't it say that you have to solve for y at the end? So what we have right now is, okay, if you take the limit as x approaches infinity and natural log y, isn't it just natural log y? So we've got natural log of y equals this. So how do I solve for y? E. So e to this, e to that, you get y equals e to the first. So your answer is actually e. Now, would anyone have gotten e a different way? Because you know what's funny? I took this to the calculus teacher, you know, Mr. Antonowitz, and I was like, how do you solve this, Mr. A? And he's like, it's e. I was like, you're insane. It's the definition of e. This is the definition of e. Okay, so that'll come up later. Right now, this is how you can solve it. Okay? But yeah, it's the definition of E. So if you ask Mr. Antonowitz, he just looks at it and goes, oh, that's E. This one down here, however, you can't just solve. Okay? So that one, that's not a definition of something. So this one here, you would actually have to work out. I'm going to give you guys kind of a head start to think about how to do this. It's the same steps as up here. So I'm going to give you a few minutes to start working through it. He just, yeah. Yeah. Because I was trying to figure out, I think it might be in a different lesson, like how to solve this problem, because it was like the book was telling me it was E, and I was like, I have no idea why that's E. And he's like, it's E. It's just the definition. And I was like, okay, apparently that's something I missed. I don't know. But apparently it's just something you're supposed to know. So yeah, we will memorize it later on when it is a little more relevant to what we're doing. But for now, we would solve it using this, taking the natural log both sides. So I'll let you guys start number 8, and we'll start it in just a couple minutes. That way we are sure to get through it here. Okay, so first thing you want to do is set it equal to y and take the natural log. And then you'd pull that x down front, and then we're going to take the limit as we're approaching 0. Oh, sorry. Yeah, this, whenever it's the right, it never shows that line up and down, so thank you. Which will probably be important in a moment. So did you guys move this to the denominator just like the other one? So in the numerator, we've just got the sine of x, and that x got pulled down front, so I'm going to put that into the denominator. Okay, and if you're plugging in 0 from the right, oh, this is natural log, I forgot. That would be important. Okay, I was going to say, how does this work? Sine of x, as you're approaching 0 from the right, is sine positive or negative? So think of a sine curve. This is what's going on in my head right now. So as I'm approaching from the right, it's approaching 0 from the positive side, right? So it's slightly positive. So then think of natural log graph. Natural log graph looks like this. So as I'm approaching 0 from the right, it's slightly positive. It's going to negative infinity. And then here, if I plug in 0 from the right here, I get 1 over really, really small, so infinity. So plus or minus infinity over plus or minus infinity, I can apply L'Hopital's. So questions on that at all? Okay. So let's go ahead and apply it here. So now I've got the limit. The derivative of natural log of sine is 1 over sine times cosine. So I've got cosine over sine, which I'm just going to leave like that. You could write it as cotangent, but it's actually going to make it more difficult. So the denominator, negative 1 over x squared. And then I'm just going to, instead of divide by this, I'm going to multiply by the reciprocal. So I'm not using L'Hopital's here. I'm just cleaning it up. And the reason I'd leave it as sines and cosines is because those are easier typically for us to deal with. So negative x squared cosine of x look okay on top. And then sine of x on bottom. As we approach 0 from the right, the top is 0 because of this piece, and the bottom is 0 because sine of x goes to 0. So we've got 0 over 0, therefore L'Hopital's. Everyone okay with that? Okay, and then we apply L'Hopital's here again. And now what do I have to use on the top? Product rule, so leave negative x squared alone. Multiply by the derivative. That looks terrible, whatever. And then you're adding that to negative 2x times cosine x stays left alone. And the derivative of the bottom is cosine. And if you plug in 0 now, you get 0 over 1, so you get 0. And a lot of people circle that. What do you have to do to finish this out? Set natural log of y equal to 0. So what is y? 1. E to the 0, right? Anything to the 0 is 1. So your answer there would just be 1. Cool, huh? Yeah. Okay, so homework here. Okay, I used to write it as an equation because someone at an AP conference said it was fun and they liked doing it. I was like, that does sound fun. And then people were doing the wrong problems like all the time, even though that's like a basic linear function. It should be easy to plug into, but whatever, you know. So it's 7 to 67, every other odd, and then 73, 93, 97. Don't do 27. That's not one that we know how to do. And that's my signature if you need to forge it for anything, okay? Okay, cool.